Welcome to the Deep Dive, the single most efficient way to access the knowledge that truly separates the informed professional from the casually aware. If you're operating in a high-stakes, complex field, and software development is definitely one of them, the traditional route of just drowning yourself in endless technical manuals and reading every single commit history, it simply isn't feasible. You need a strategic shortcut. You need a set of disciplined practices that fundamentally guarantees quality design and, most importantly, certainty. The knowledge we've stacked for you today comes directly from decades of professional texts, research, and industry experience, and it all culminates in a strong, near-unanimous verdict on a practice that, for a long time, was considered optional or even, controversial.
That's precisely right. Our deep dive is focused entirely on test-driven development, or TDD, and we are here to provide the synthesis of evidence that moves TDD out of the category of nice coding style and into the realm of, well, essential professional discipline. Our mission today is pretty comprehensive. We'll first trace the surprising origin story, a revelation in the late 1990s that demonstrated the raw, immediate productivity gains of TDD. Second, we are going to meticulously break down the core mechanics, the three simple, non-negotiable laws that govern the process. And most importantly, we are going to synthesize what the source is called the litany of benefits, demonstrating precisely why this discipline creates unparalleled technical certainty, psychological courage, superior documentation, and demonstrably better software design.
And to start this journey, we have to travel back to 1999. We're going to witness an anecdote involving a 30-year veteran programmer, someone who had seen it all, and who expected to just dismiss TDD out of hand. But what he saw, a 30-second rapid-fire coding and testing cycle, it completely floored him. It flipped his entire understanding of what real engineering in code looked like. Okay, let's unpack this.
To really appreciate the moment of revelation, you have to understand the technical climate of 1999.
Yeah, the context is everything.
It really is. So the setting is Medford, Oregon. The author of our source material, a grizzled professional programmer, he traveled there to observe Kent, a figure associated with a discipline that was just starting to solidify into what we now call TDD. The author's background is crucial here, 30 years in the trenches. That means he carried the accumulated wisdom and, frankly, the cynicism that comes with watching technology trends just flash and then fade.
So he's seen it all before. He's not easily impressed.
Not at all. He approached the meeting with massive skepticism, completely ready to categorize TDD as just another coding fad that would be gone in a year.
And his skepticism was entirely rooted in the old normal.
Yeah.
The operational reality of industrial strength that compiled languages like C++ or even the early days of Java.
Right.
Think about the programming cycle time in those days. It was slow, it was laborious, it was, as the source describes it, absurd compared to the quick feedback TDD delivers.
It was a whole different world. You would spend a significant amount of time, maybe an hour, maybe even more, just writing dozens or hundreds of lines of complex production code.
All in one go.
All in one go, just holding it all in your head. And only then would you initiate the process. Compile, link, and finally, run the executable.
And that entire cycle could take minutes, sometimes tens of minutes, depending on the complexity of the code base.
It was a waiting game, a very frustrating waiting game, and inevitably, the first run would fail, just spectacularly. And then you would enter this grueling debugging phase, trying to reverse engineer, where in those hundreds of new lines of code, your assumption went wrong.
It's like looking for a needle in a haystack you just built.
Exactly. The standard operating assumption was that serious, high-level, compiled languages simply required the slow, long, tedious cycle as the cost of producing powerful, efficient software. That was the trade-off.
Which brings us to Kent's method. So the author sits down, ready to tackle a small coding problem, and he's prepared to start writing the production code, the actual function needed. But Kent refused to write the silly thing first.
He stops him right there. And instead, Kent adopted this disciplined, almost ritualistic approach. He first wrote a very, very small unit test.
And we are talking minimal code here.
Tiny. Just enough to define what the desired behavior should be. And that unit test naturally failed instantly because the production function it was calling didn't exist. Or if it existed, it certainly didn't behave as the test demanded.
And not compiling, in this context, that counts as failing.
It's the first kind of failure, yes. So only after seeing that specific, immediate failure did Kent write just enough production code to satisfy that one tiny, focused unit test.
And just enough, not a line more.
Not a single line more. And once the test passed, he would immediately write the next small failing test and then the next minimal piece of production code to make that test pass.
This was the moment of shock.
Yeah.
The veteran programmer was used to the 1-hour block before compilation, just this long, long period of writing.
Right, the big batch.
And Ken, however, using this tight, self-imposed discipline, was executing his code, seeing results, and cycling through the process of writing, failing, fixing, and passing every 30 seconds or so.
30 seconds.
30 seconds. It's hard to overstate how revolutionary that was. It wasn't just faster, it changed the entire cognitive load.
Completely. You went from holding a huge block of untested code in your head for an hour just praying it would work.
Praying it compiles on the first try, which it never does.
Never. And you go from that to focusing intensely on one tiny requirement at a time, receiving immediate, constant confirmation that you're on the right track. The author was quite literally flabbergasted by the sheer speed of iteration.
I bet. It's a completely different way of thinking about building something.
And the realization of why it was so productive brought an interesting connection to the past. The author realized this 30-second cycle was the kind of high-speed feedback he had only experienced using interpreted languages decades earlier.
Oh, interesting. Like BASIC or Logo?
Exactly like BASIC or Logo. Think back to those environments. There was no compile step, no linking phase. You added a line, you executed it, you saw the result, and you moved on.
Instant feedback.
That rapid, instantaneous feedback loop was the engine of productivity in those interpreted systems. It's why so many people learn to code on them so quickly.
But that speed was sacrificed as soon as developers moved to the industrial-strength compiled languages, right?
Yeah.
You traded that speed of iteration for performance and power.
That was the accepted wisdom. You give up one to get the other.
So the profound takeaway from that trip to Medford was that TDD was not just a testing practice. It was a simple yet strict discipline that allowed coders, using powerful, real languages like Java in this case, to effectively recapture the incredibly high productivity and quick feedback loop previously associated only with those older interpreted environments.
It was the best of both worlds.
By forcing the developer into those tiny, self-contained cycles defined by the tests, TDD eliminated the hours of frustrating, complex debugging, replacing it with seconds of focused execution.
It fundamentally proved that the slow cycle time wasn't an inherent requirement of professional compiled languages. It was merely a symptom of the lack of adequate discipline.
So it was a process problem, not a technology problem.
Exactly. TDD provided the necessary structure to break down massive problems into microsteps, each immediately verified. And that, ultimately, is the foundation. It moved TDD from being an experimental technique to being a mandatory professional standard for anyone seeking to maximize output and quality simultaneously.
Here's where it gets really interesting, because the sheer productivity implied by that 30-second cycle sets up the present-day verdict. TDD moves from being an option to a core professional expectation. So now we jump forward. We've seen the genesis, that moment of revelation. After decades of practical application and just a mountain of corroborating data, the professional texts offer a strong, conclusive verdict on TDD.
The verdict is in, and it is unambiguous. The sources draw a sharp, almost provocative comparison that frames TDD's status perfectly.
What do they say?
They state flatly, GOTO is harmful and TDD works.
Wow. Okay, so we should pause on this analogy for a moment because that is a very strong statement.
It is. For those not deep in the history of programming, the GOTO statement allowed a program to jump arbitrarily to any line of code.
It created what they called spaghetti code, right?
Exactly. Unstructured, unmaintainable, logic-defying systems. And decades ago, the computing world achieved a hard-won consensus that GOTO was fundamentally destructive to clarity and reliability.
It was forbidden practice.
It was. So by equating the proven efficacy of TDD with the proven detriment of GOTO, the text signals that the debate is over. TDD is not merely favored, it is an established truth of responsible engineering.
And this leads directly to the core philosophical driver of TDD professional responsibility.
It does. The discipline forces every developer to answer a foundational question.
Which is?
How can you, in good conscience, consider yourself a professional if you don't have objective, verifiable proof that all the code you just wrote actually works?
That's a heavy question. And perhaps more critically, how can you confidently make a structural or functional change to that code base or to a feature you wrote 6 months ago and be absolutely sure you haven't broken some obscure dependent function elsewhere in the system?
The only acceptable answer to those questions, according to the professional literature, is the routine use of automated unit tests with demonstrably high coverage.
And TDD is just the way to get there.
TDD, by its mechanical nature, is simply the most efficient and effective process for ensuring you achieve that high coverage and the resulting robust architecture.
So let's look at the mechanism itself. You said TDD is rigidly defined by three deceptively simple laws.
Yes. These rules are not suggestions. They are constraints that lock the developer into that highly productive short cycle time we discussed earlier.
Okay, let's detail these, because adhering to these laws is what separates true TDD from just, writing tests whenever you feel like it.
It's the core of the whole discipline.
All right, so Law 1, you are not allowed to write any production code until you have first written a failing unit test.
This law is the foundation. It establishes the priority. The definition of the required behavior must precede the implementation of that behavior.
The test is the specification.
Precisely. Without a failing test, you are just coding into the void based on assumptions. You're guessing.
Okay, Law 2, you are not allowed to write more of a unit test than is sufficient to fail, and not compiling is failing.
This is the law of minimization for testing. It stops you from getting ahead of yourself and writing some complex, brittle test for a feature that doesn't exist yet.
You're not trying to test the entire system at once.
Not at all. You write only the smallest possible test case, maybe just the function signature, knowing it will instantly fail compilation because the function hasn't been written yet. This keeps the tests focused and highly specific.
Makes sense. And finally, Law 3.
Mm-hmm.
You are not allowed to write more production code that is sufficient to pass the currently failing unit test.
And this is the mirror image, the law of minimization for the solution. It directly combats the natural tendency of programmers to code ahead.
To get clever.
Exactly. To generalize the solution, to add future features, or to write code for requirements that haven't yet been defined by a failing test. This constraint is critical because it forces you to implement only the current necessity, avoiding bloat and untested logic.
Let's dig into the professional danger of breaking that third law of writing too much code. What really happens?
When you code ahead, you inevitably introduce untargeted code. This means you are writing logic that is not currently verified by any existing test. You might think, oh, I'll write the test for this later, but in that moment, you have created a gap of untested assumptions.
A blind spot.
A huge blind spot. And the danger is insidious. When you write untested code, you create a potential source of failure that the test suite won't catch. Furthermore, writing generalized code often leads to high internal coupling.
What do you mean by that?
The components within the function start to rely too heavily on each other. It becomes a tangled mess, which makes it exponentially harder to break out into testable units later on. You're essentially building complexity without external verification, which is the antithesis of professional engineering.
So adherence to these three laws mechanically locks the developer into that famous red-green refactor cycle, that 30-second loop we talked about.
That's the one. You start by writing the smallest bit of test, and that fails. That's red.
Right.
Then you write the smallest bit of code to make it pass. That's green.
And then, crucially, you clean up the code, confident the test will catch any regression.
That's the refactor step. And you just go around and around that loop every 30 seconds. This continuous rapid cycling creates a fascinating growth pattern in the codebase. The production code and the test code streams, they grow simultaneously in what the professional texts term complementary components. They are developed in absolute lockstep, always reflecting and supporting each other's boundaries.
So they're like two sides of the same coin.
A perfect way to put it. And the powerful analogy offered in the sources is that the two code streams fit the production code like an antibody fits an antigen.
Okay, that's a very specific biological analogy. Let's break that down.
It's specific for a reason. This fitting implies two critical things for the code: isolation and specificity. An antibody is designed to recognize and target one specific antigen.
Oh.
In programming terms, the unit test, the antibody, is custom designed to recognize and interact with one specific piece of production code, the antigen, and only that piece.
This specificity ensures that the production code is isolated from other concerns. It confirms its functionality without relying on the state of the surrounding application.
And that inherent forced isolation is the mechanical genius of TDD. It's the secret sauce. And it's what sets up all the later design benefits we're about to talk about.
So the mechanics are simple red-green refactor in these microbursts. But the true mandate for TDD lies in the measurable, powerful outcomes. The synthesis of evidence points to a litany of benefits that transforms quality, speed, and even the psychological experience of professional coding.
Absolutely. The first and most important benefit is the foundation of the whole system: certainty.
Certainty.
TDD is fundamentally a professional discipline focused on eradicating fear and maximizing confidence. If you adopt this discipline, you are not waiting for a weekly build server to run tests. You are running tests dozens of times a day, hundreds every week.
That certain verified feedback loop is what allows a complex system to remain agile. To illustrate this certainty, let's look at the concrete example provided in the source material, the experience of maintaining a tool called Fitness.
Right, so Fitness is a Java-based acceptance testing tool, and it's a substantial application. We're talking 64,000 lines of production code.
So it's not a toy project.
Not at all. But the key takeaway is the volume and speed of its testing regimen. The Fitness maintainers have written 28,000 lines of test code alone, spread across over 2,200 individual unit tests.
2,200 tests.
And this testing suite covers at least 90% of the production code base. But here's the metric that should shock you. Running this massive, comprehensive suite of over 2,200 tests takes only about 90 seconds.
90 seconds. That is the measure of professional certainty. If a developer needs to introduce a change, maybe fixing a complicated edge case deep inside the system's core logic.
Right, the scary kind of change.
The scariest kind. They can make that change, commit it, run the full 90-second test suite, and if it passes, they have near certain confidence that they haven't broken any established functionality anywhere else.
That speed is not accidental. It is a direct consequence of the discipline design TDD enforces. The only way to run 2,200 tests in 90 seconds is if those tests are isolated, fast, and highly decoupled, which validates the core design benefit we'll discuss shortly.
Because the tests are designed to function independently, that antibody model you mentioned, they can be executed rapidly and in parallel.
Exactly.
And that confidence translates directly into the shipping process. The source notes that the QA process for Fitness is, well, simple. The command and release.
That's it.
This command executes the build and, crucially, runs all 2,200 unit and acceptance tests. If they all pass, they ship the code. That is an almost unheard of level of shipping confidence in a complex system.
It is. They are relying on the executable documentation, the tests, to be their primary quality gate.
Which naturally leads to the second major quantifiable benefit, a vastly reduced defect injection rate. This is where the return on investment truly shines, isn't it?
This is where it hits the bottom line. Let's define this clearly for those less familiar with the metric. Defect injection rate refers to the number of defects introduced into the code base per unit of code written or per unit of time. A low rate means high quality.
So in the Fitness case, despite the team adding 20,000 new lines of code in 1 year, their bug mailing list contained only 17 bugs in total for that year.
17. And many of those were just cosmetic issues, not critical failures. That is an exceptionally low defect injection rate for a system of that complexity and scale.
But this isn't just an isolated anecdote from one project, is it?
Not at all. This is where it gets really compelling. The professional literature cites multiple studies and reports from major corporate environments that confirm TDD's impact.
We're talking about major industry players here.
The biggest: IBM, Microsoft, Sabre, Symantec. Teams within these companies, when strictly applying TDD, experience defect reductions of 2x, 5x, and astonishingly even 10x.
10 times fewer bugs.
A tenfold reduction in the number of bugs you introduce is not merely a technical tweak, it is a fundamental shift in business efficiency and engineering integrity.
I mean, that means less time spent firefighting, less technical debt accruing, and more predictable project delivery.
It's a massive competitive advantage. When data consistently shows you can reduce errors by a factor of 10, ignoring TDD ceases to be a coding decision and becomes a professional liability.
And this quantitative quality leads directly to the third, and I think maybe the most interesting psychological benefit: courage.
This one is huge. Every professional programmer knows the feeling of staring at a particularly messy, complex function, maybe something dating back years, a real hairball of logic.
Oh yeah, the code nobody wants to touch.
Exactly. The internal professional instinct screams, clean this up, refactor this mess. But that instinct is almost instantly overruled by fear.
And the fear says, I'm not touching it. If I touch it, I might break some hidden dependency, and I'll be the one spending the weekend debugging.
This fear is the primary engine of technical debt accumulation. The code needs cleaning, but the risk associated with cleaning it is too high, so the code just rots, becoming harder to understand and maintain over time.
TDD provides the antidote to this fear by guaranteeing the certainty we talked about.
It's the direct cure. If you have a trusted, fast-running test suite that covers 90% of the code, that fear just evaporates. You gain the courage to act.
So you can refactor that tangled function into simple, clear components, and within 90 seconds, confirm that you haven't introduced a single regression.
But that's an excellent point to probe. If the tests run in 90 seconds, why couldn't a programmer just write tests later and still gain that courage?
Yeah, what's the difference?
The difference lies in trustworthiness and architectural enforcement. When you adopt TDD, the discipline ensures the tests are written and that the architecture is designed to make those tests fast and trustworthy.
Ah, so you can't get that speed without the design.
You can't. If you write tests later, the code you are testing might already be highly coupled and untestable, meaning the tests you write are slow, cumbersome, or only cover high-level integration points, not the individual complex functions inside.
So the courage is just an operational side effect of a structure that was guaranteed by the TDD process itself.
Exactly. And when developers have this courage, the professional techs observe that the codebase sculpts into simple and pleasing structures, which fundamentally enables agility and long-term sustainability.
Okay, so this leads to the fourth profound benefit, which is often understated: documentation.
Right. When we think of documentation, we usually picture those dense manuals.
The 27-page glossy manuals full of paragraphs and colorful diagrams explaining configuration steps. But let's be honest, if you are a programmer trying to understand how to use a function or a third-party framework, you skip those pages.
Every time.
You go straight to the appendix, the section with the actual code examples, because the code examples are unambiguous. They show the truth of the system's usage, not just the intention.
This is where TDD elevates unit tests to the best form of documentation. Unit tests are those code examples, written in code, describing exactly how the system is intended to be used at the lowest level.
So they define the required inputs, the expected outputs, and the specific behavior of every function and every object within the system.
And unlike that glossy manual that becomes outdated the minute a developer touches the production code, unit tests are unique in their quality. They are, 1, unambiguous because they are executable code.
2, they are accurate, because if they are not accurate, the test suite fails and the code is not shipped.
And 3, they are executable, meaning they are living, verifiable proof that the documentation is correct. They can't lie.
In essence, they are the low-level design document of the system. The source explicitly calls them the best kind of low-level documentation that can exist. What professional would settle for passive aging documentation when they can have a living executable manual that confirms the system's correctness every time they press run?
It's a great question. Which brings us to the final and maybe the most strategic and far-reaching benefit: design.
The design of the code itself.
Yes. When you are strictly adhering to the 3 laws of TDD, particularly Law 1, write the failing test first, the developer is forced into an immediate healthy conflict. You know the grand solution you want to build, but you are required to define the isolated failure first.
The inherent challenge of testing any complex code is isolation.
No,
Right.
it is. If you have a massive main processor function that calls database connector, which in turn calls logger, how do you test main processor in isolation without needing a live database connection and a functioning logging system?
You can't. Not easily. It would be slow and brittle.
To test main processor effectively and quickly, you must be able to decouple it from its dependencies, the database and the logger. You have to figure out how to substitute or mock those dependencies so the test only verifies the logic inside the main processor.
This is the critical driving force. The necessity of writing a failing test first forces you to think critically about good, decoupled design immediately.
The code must be testable, and testable code must be isolated, modular, and adhere to clean architectural boundaries.
So let's contrast this with the alternative, what you call the coupling trap.
If you write the production code first and worry about tests later, there is zero pressure to decouple your functions. The developer naturally relies on neighboring functions, creating hard, tight dependencies.
You end up with untestable, monolithic blocks of code.
Exactly. You might manage to write high-level integration tests that check the input and output of the massive block, but you certainly won't be able to test the individual complex logical paths deep inside it.
And the professional costs of the coupling trap are immense. Highly coupled systems are fragile, they're expensive to change, they are the very definition of technical debt.
And TDD, by forcing you to solve the isolation problem up front, by demanding you think about how to mock dependencies before you write the implementation, is a powerful force driving developers toward better modular architectures.
This structural benefit is why TDD is so important for modern practices like microservices or domain-driven design, which absolutely rely on strict, clean boundaries between components. TDD ensures those boundaries are established from the first line of code.
It is an external mandate that drives modularity. And truly, what professional would willingly avoid employing a discipline that automatically pushes them toward demonstrably better, future-proof designs? So, the litany of benefits, the certainty, the 10x defect reduction, the courage, the executable documentation, and the superior design, it really does make an overwhelming case.
It does. But, as we promised, it is vital to clarify what TDD is not, because no discipline is a universal panacea.
That's right. The professional texts are very clear on this. TDD is not a religion, nor is it a magic formula.
So adhering to the 3 laws does not automatically guarantee success.
No. A developer can still write bad production code, or, just as damagingly, write bad, weak, or superficial tests, even when following the test-first rule. It requires skill, judgment, and intent, not just ritualistic adherence.
The most critical conceptual distinction we must fully articulate, then, is the difference between writing tests afterward, which is sometimes called test-last development, and writing tests first, which is TDD.
And we frame this as the difference between defense and offense.
Okay, defense versus offense. Explain that.
When you write tests later, you have already solved the problem. The solution is fully structured, the functions exist, and the logic is implemented.
Right, the code is done.
The test you write at this point is a test written after the fact for defense. Its purpose is to measure the boundary of the existing code and protect it with coverage. This is a valuable high coverage defense, but it's still defense.
Got it. So what is offense?
Tests written first, following the 3 laws of TDD, are offense. They are written when the problem is not yet solved, and the test itself serves as the functional definition of the solution. You are defining the path forward by first defining the desired behavior.
The crucial structural difference, then, is that after-the-fact tests are never as incisive as tests written first.
Never. When you, the developer, write a test for code that already exists, your mind is inherently biased. You already know exactly how the code works, what path the data takes, and what assumptions you made during implementation.
And this inherent knowledge makes it incredibly difficult to write truly comprehensive, thorough tests that successfully probe every edge case, every hidden assumption, or every flaw in the design.
Your test writing is subconsciously guided by the solution you already created. You test what you know works, not necessarily what might break.
But TDD, by contrast, forces the developer to define failure before success. You are sitting there, cold, defining the problem in measurable, concrete terms without having yet written the solution.
And this ensures the tests are focused, deeply incisive, and truly drive the design, rather than just validating the finished product. This offense-first approach is paramount to achieving the design and quality benefits we've detailed.
So the summary remains solid. TDD is the professional option. It is a strict, intentional discipline that fundamentally enhances certainty, courage, defect reduction, superior documentation, and force decoupling in ways that writing tests later simply cannot replicate.
But the sources do include a final necessary caveat.
Right. There are rare times when following the 3 laws is genuinely impractical or inappropriate.
Yes, examples include certain highly complex external integrations, such as interacting with third-party hardware or legacy UIs that resist isolation, where the overhead required to rate a meaningful, fast unit test outweighs the immediate value.
The guidance here is crucial. A professional developer must always maintain judgment and should avoid a discipline when it would clearly do more harm than good.
But these are described as rare situational exceptions, not a reason to abandon the discipline entirely for the 95% of code that benefits from it. The overwhelming weight of evidence confirms that TDD is the responsible, professional approach to coding complexity. So let's bring this incredible deep dive back to you, the learner. We started with a foundational history lesson, witnessing a 30-year veteran gasp at the revelation of a 30-second cycle time in 1999, the realization that discipline could bring interpreted language productivity to compiled giants.
We established that TDD is not up for debate. The verdict is conclusive. And we detailed the quantitative and psychological returns. Quantitatively, the data from major players like IBM and Microsoft showed verifiable defect reductions of up to 10x. Psychologically, TDD provides the professional courage necessary to aggressively tackle technical debt and maintain the integrity of the codebase. It is a discipline that delivers measurable quality and verifiable living documentation.
TDD is fundamentally about choosing rigorous discipline to guarantee quality and design integrity. It proves that small, constrained steps executed frequently lead to vastly superior outcomes than large, infrequent, untested pushes. And if knowledge is most valuable when understood and applied, and this deep dive shows TDD creates executable, low-level documentation that structurally forces better design, well, the philosophical implications stretch far beyond the realm of software.
Which brings us to the final provocative thought we want to leave you with, something for you to mull or explore on your own. TDD's unit tests function as living, executable, low-level design documents that prove the system works correctly. They are the ultimate guarantee of certainty in a mutable, complex system. If that is true, what analogous executable documentation, what verifiable self-checking system could non-software fields such as civil engineering, complex financial modeling, or regulatory compliance develop to similarly guarantee certainty, force better design, and enable fearless, proven change? Thank you for joining us for this deep dive into professional discipline. We'll see you next time.